Well, as we always do in physics, we're now going to take that law of momentum conservation and start solving problems mathematically with it. The important key to remember in these problems is that we're looking at a system, and in the system that they give us, we have to determine whether momentum is conserved. If it is, then we don't have any problems usually working the problem itself, assuming that momentum is going to be conserved. Okay, so when we have some sort of a collision take place, or if we have one item launching another item, these are the types of problems we're going to be working here. If you have one item launching another one, there is going to be conservation of momentum, and after the launch takes place, before a launch, you have no momentum at all. After the launch, one object is going to move one way, the other object is going to have to move the other way, so that the sum of the two momenta is still going to come up to zero. Our family is a big hunting family. I have a number of sons, and they all enjoy hunting deer and squirrel and rabbit and all kinds of different critters. And so we're all familiar, at least in our house, with the kick of a gun. You fire a gun, and then if you're holding it, that gun's going to kick backward and hit you as well. And so you've got to be prepared for that when you fire a shotgun or a rifle. And so firing any type of a gun, firing a cannon, the firing of a rocket into space, all of these involve the topic of recoil velocity, which basically means it's that backwards movement that happens when one object launches another object. So again, with guns that are being fired, with cannons that are being fired, with rockets that are being launched, any type of launching of an object is going to involve recoil velocity. So let's start out by looking at example 9.4. And it says a 4.5 times 10 to the 5th kilogram cannon is mounted on wheels that are free to roll. So when it tells us that, it tells us that movement is not going to be inhibited at all. And so it does tell us later on that the friction is not going to be an issue in this problem. So the cannon fires a cannonball, and it gives us the mass with a horizontal velocity of 145 meters per second. Assuming that friction is small enough to be ignored, which we're going to ignore it in this problem, what happens to the cannon after the shot is fired? He didn't tell you that he really wanted a quantitative answer, but he does here. And so what we know is that we're looking at a system of a cannon and the cannonball. And so the momentum of the system before and the momentum of the system after have to be equal. So I can look at that mathematically as momentum before is equal to the momentum after. And I have to look at the momentum of the entire system. So if I look at the momentum of the cannon before, and I add that to the momentum of the cannonball before, which I'm just going to abbreviate those two things, cannon with the C and cannonball with the CB, that is going to have to be equal to the momentum of the cannon afterwards plus the momentum of the cannonball afterwards, okay? Before the launch happens, neither the cannon nor the cannonball are moving. So this side is going to be 0. The momentum of the cannon is its mass times its velocity. So the mass of the cannon, they told me, was 4.5 times 10 to the 5th kilograms. And the question is, what happens to that? So I don't know the velocity of it. The mass of the cannonball was 1.2 times 10 to the 1st kilograms, and I know that its velocity was 145 meters per second. Okay, so when I solve this equation, obviously I'm going to multiply this, I'm going to move it over to the other side, at which point it becomes negative, and then I'm going to divide both sides by this mass. I'm going to assume that you know how to how to manipulate all those numbers. Once I do that, that's going to give me a velocity that is negative of 0.0038 meters per second. So what does that mean? That means that the cannon is going to go, the cannon, turn this way so I get everything the right direction. If the cannon is here, the cannon shoots the cannonball this direction at 145 meters per second. The cannon is going to move backwards at 0.0038 meters per second. Now, obviously, that's not very fast at all. And the reason is because the cannon is so much more massive than the cannonball is. So it doesn't move backwards very fast. The velocity is not that big. But together, these two momenta have to add up to 0. So that's why you have to have one going one direction, one going the other direction. That's your recoil velocity that the cannon is experiencing. Okay. We also want to go up and look at example 9.5. And both of these examples are examples where you have a collision or a meeting of objects, and after the collision, the two objects become united as one. And so the first example is of a car collision. And so we've got two cars, and they're going opposite directions. They slam into each other head on. They all get crunched together, and then they will continue moving. Now, I want to point out that in this problem, we're actually being quite unrealistic, because the friction, it says the friction between the road and the car is small enough to be ignored, but there are some things that he also ignored that he didn't mention that he was ignoring. One thing that he's ignoring is that part of the energy with which they hit is going into sound energy, because we all know there's always a loud noise when you have a collision. And you're also going to have a lot of that energy going into the deformation of the car. You're going to have all that crunching metal, and it takes energy to deform all of that. So it's not exactly as simple as he lays it out, but we're going to go ahead and work the problem under those assumptions anyway. I just wanted to point out that some of the energy that's involved in that collision is actually being transferred into another type of energy that we did also ignore. Okay, so once again, the momentum before has to be equal to the momentum after. So I'm going to have the momentum of, I'm just going to put the first car plus the momentum of the second car is going to be equal to the momentum of the two car system after the collision, because they do collide and become one unit. So the first car is 675 kilograms. That's its mass, and it is moving with a velocity of 19.3 meters per second. Okay, so that's car 1. Car 2 has a mass of 895 kilograms, and it has a velocity of negative 22.1 meters per second. Now, why did they say it was negative? Remember, the negative sign indicates direction. This car's moving one way, this car's moving in the opposite direction. Before we actually go ahead and work this problem out, I want you just to put your thinking cap on. You have this car moving this direction, this car moving this direction. Notice, first of all, which car is bigger. This one is. This car has more mass. Which car is moving faster? Again, this one is. And so, based on just your knowledge of how things normally work, once the cars collide, which way do you think the two-car system is going to be moving? Is it going to be moving the same direction as this car was? Or is it going to be moving the same direction as this car was? I'm not going to answer that yet, but I want you to think about it, and then when we get done here, we'll see if you're correct. Okay? The two-car system, then, is going to have a combined mass of 675 kilograms plus the 895 kilograms of the second car. So we have to combine the masses together. and then the two of them together will have a velocity, and that final velocity is what I'm trying to find. Okay? Now, once again, I'm going to assume that you are perfectly capable of doing the algebra and solving this problem. Obviously, you're going to multiply these. You're going to multiply these. Watch your negative sign. You have to add them together, and then you're going to end up with positive or negative number here. Well, hopefully you can tell just by looking at it, it's going to be negative because this is going to be bigger. Then you're going to divide by this total mass on this side. And so when you do that, you should come up with a final velocity of a negative 4.3 meters per second. So if you said just a second ago that the two-car system after collision would be moving the same direction as the second car, then you were right. And again, it's because this car was bigger and it was moving faster. So combination of those two things, because its momentum was larger, the two-car system at the end is going to be pushing it in that direction. Okay? All right, so that takes care of that one. And then there's one more here. An empty truck slowly moves under a grain hopper. The hopper dumps grain into the truck until it is full. The hopper puts 7.4 times 10 to the 2 kilograms of grain into the truck, and the driver allows the truck to coast while it is under the hopper. What will the truck's velocity be when it was full? We're assuming that we can neglect friction. Okay, so this setup is going to look very similar to the setup that we just used, because we know that the momentum before has to be equal to the momentum after in our system. And so in this case, we're going to have, in place of 1 and 2, we're going to have the momentum of the truck plus the momentum of the grain, and then afterwards we're going to have the momentum of the entire system. Okay, so the momentum of the truck before, the truck's mass is 1,200 kilograms, and it is moving with a velocity of 2.2 meters per second. Okay, the momentum of the grain. Now, I do want to point out again, this grain is falling, and yes, it does have momentum, but that momentum is in a downward direction, and we're talking only about our horizontal direction. So the momentum that it has going down isn't going to have an effect on how the truck is moving this way. Okay, because remember that if you split vectors up, you have to look at the direction that those vectors go. So the horizontal component of this of the grain's movement is going to be 0, and we're only looking at that horizontal component. So the grain has no momentum in the horizontal direction. The total momentum of the system afterwards is going to be the mass of the truck plus the mass of the grain, which was 740 kilograms. And you'll notice here, he did give those to me in scientific notation, but I have just as many significant figures when I write them this way as when I put it in scientific notation. And I think it's easier to do it that way in place of putting it in scientific notation if I don't have to. So the combined mass of the system is these two numbers, and then that combined system is going to have a velocity, which is what I'm looking for. Okay, so once again, you're going to do your multiplication. You're going to add that to 0. You're going to divide both sides by the combined mass, and then that will give you a velocity of 1.4 meters per second. Now, that should make sense to you because once I increase the mass, since momentum is mass times velocity, if the momentum is going to stay the same and the mass goes up, the velocity is going to have to go down in order to keep that value constant. Okay, so those are all problems where we are dealing with conservation of momentum, and you're going to get lots of practice with these types of problems.